How much time? Okay, okay. Yeah, yeah. All right. Okay, thank you. I'm happy to be here, and thank you to Dario who began this session. I'm lucky because many of the concepts I'm going to touch were already touched by him. So, namely Zen and shared caches. But first I want to give you a glimpse of the project I'm involved in with well, my lab in Modena and evidence here in Pisa. The project is called I-MECH, and we have many other partners with us. It's focused on industrial automation, which is an interesting, I think, field for real time. Also from a strategic point of view, because there are many different custom tailor solutions, many operating systems, and here I think the open source can make a difference in the long term in providing something more interoperable and more open. So I'm very happy that we have so many big names with us, like Philips or GMV, some Italian companies. Each one of them brings a specific application. We range from I don't know, a medical manipulator is a kind of bed where the where people just you know, lies, and an X-ray operator behind a glass can move a huge arm around the person for doing X-ray scans. So from this up to teabag machines, they are crazy fast machines which produces dozens of tea bags. They fill it and they close it and they pack it in a matter of a fraction of seconds. So it's a challenging field because they have true challenge for performance on one hand and on predictability on the other, because they don't want to stop the machine because something is going bad, or cut the head of a patient, you know. Okay, the philosophy is important here, at least that's what we aim at. The thing we are building is meant to be something super modular, super interoperable. We want to standardize the way the upper layer, the way a software engineer programs the platform independently from the kind of hardware, the specific control hardware or sensors that we have. So the central object here, this building block, this big one, is the one I am interested, and we all are most interested in, I guess, which is the computing platform. And this platform is growing from the requirements of all these partners. Here I collected the most significant ones. They all are using, well, almost all, x86 architectures, ARM or RISC-V or embedded segment are kept for the lower end, the simplest components. The central one instead, it has to be an x86 based, at least a quad core, and we have a constraint also on the price. As I told you, they do have a pretty demanding constraint. They want, for instance, to have closed loop latency in for given tasks. For given tasks, 100 under 100 micro, which is not what people dare to do, not even closely, on other applicative domains like autonomous driving or flying. In that cases, you have more maneuver margin. From the software point of view, the big choice that we have made with the partners is to have a real-time operating system on top, possibly, replaceable with something custom, and a hypervisor on the bottom. Again, possibly interchangeable. We need Simulink integration. They don't really program. They just draw a model, and they usually generate the code, some tuning, and then it's done. We want EtherCAT interface. Well, they were asking for a dozen of different protocols. We chose the most liked one in the requirement table. And speaking of the hypervisor, they want a plethora of possible guest operating systems, and of course they want to manage different criticalities on the same platform. So some real-time thing with some human interface on another. Let me first tell you about the operating system. We've chose, of course, Erika, which is the product of evidence. It's a project born for automotive. It's AUTOSAR compliant. It's certified by the usual standards in the field. It's very tiny. One might think it's just a library around your tasks. It's very small. It's open source, and it's already used by several companies like Magneti Marelli or Piaggio, Vodafone Automotive. The missing bits that we needed to add were, well, the EtherCAT interface. That was the first challenge. The guys from Evidence imported an open source implementation, and it was kind of doable. More painful, as far as I understood, was to build the integration with Simulink, because on top of the hypervisor we need to have the host which generates the code, and then we need to inject the generated binary as a task on the other code. So a small protocol for a small API has been defined on top of the Google gRPC in order for allow the two domains to communicate in a high level way. And here is the picture of the piece of hardware we've chosen as a reference architecture. So now let's dig into the detail, and let's see how the hypervisor was fitting our needs. We've chosen Zen. I've put here an introduction, even if I'm sure that everyone knows the project. One thing I want to mention is the fact that I believe, someone in the audience will correct me if I'm wrong, I'm feeling a move toward the real-time, to the embedded needs in the last Xen development years. And one of the easy thing was the null scheduler. Why?
It's very appreciated. Everybody loved it.
If you no, let me spend a word on this. If you want the easy way, if you want to do a thing with absolutely 100% guarantees, you just partition. You waste a piece of the bandwidth from a core. Okay, I can pay this price. I know. There are better ways to do it, but this is an excellent compromise, I think. At least that's what the industry, that's what the companies want. One other interesting thing that hasn't been mentioned, but I would like to mention, is the DOM zeroless feature. It just allows VM creation, and I don't know about the precise status. Perhaps that there is some management support also, without the need of a DOM 0. So you can have, I don't know, 16 bare metals without any Linux controlling it. This is smaller. This opens the way through the way towards certification, because the microkernel is smaller than the whole Linux OS. A faster boot. It's something interesting, but is now. But for the moment, it's just for ARM. One of the problems I like to address in my daily routine is the problem of bottlenecks in modern architectures. Dario already mentioned the L3 cache, which is shared, and of course the impact in terms of performance and in terms of latency is considerable. From a real-time perspective, this means that I have either to tremendously underutilize my platform, because I want to consider, in my worst case, also a 100% miss configuration, which may actually happen, or I expose my system to unpredictable fluctuation in the performance, because of course one task miss probability depends on the lousy neighbor, as we call it.
The Intel stuff has cache allocation stuff where you can.
Yes, and this brings me to the next slide. Yes, we have. I'm going to tell you about three possible solutions. One is Intel cache allocation technologies. Many of you probably already know it. It's available on some Xeon families. We have a nice support in Zen and Linux. For instance, in Zen we can do something like CBM set, which allows us to, it's like an affinity, but for ways. So you select a subset of ways, and you say, well, these two ways can be used only by this or that core on that socket. So you can overlap things. You can have a I don't know, mutually nice tasks or VMs that run together on the same ways, or maybe no, maybe you want to separate completely. It's up to you. It works pretty well, and of course the price is that you have potentially less cache available. Of course, we are partitioning, right? And for the moment, I'm focused only on, well, the both cache, in the sense that I'm the last one. But that's an interesting remark, because when we talk about caches and problem of interference, everyone does benchmarking about data. But in some domains, I want to react as fast as possible to an interrupt, for instance, and instructions are more important there. This is an interesting bit. We in the I-MECH project, we are trying to build an open alternative to existing commercial solutions. So the obvious first step for us has been to compare with the existing ones and try to break them to later say, we are doing better. Well, actually, some of them, sometimes in a completely undocumented way, sometimes in a unclear way. Sometimes there is a reduce latency button, which does only the vendor knows what, which indeed produces a change in apparently the cache usage. We've noticed that if we enable this flag in some product or use another product, there is no cache interference on L3. And also, we observe less cache available. We have more capacity miss. So, less cache, no interference on Intel platforms with no official CAT support. I think there is a generation that I think from the 6th Intel generation ongoing, there is a undocumented support for cache technology. Perhaps this is something many already knows because they are working with Intel, and okay. But I'm not sure about the rest of the community. So our plan is to, well, just probe for this function availability, and let's use it as we can on Xeon processors. So this is a first part of the solution, but what can we do on AMD or older Intels? One of the possible solutions is to use cache coloring. I think last year a colleague of mine was talking about the same technique applied to a different domain. The idea is to exploit the fact that in the cache we have a mapping function that allows one to isolate subset of indices such that different subsets, we call them colors, different colors maps to different subset of indices in our shared cache. So if we know this bit and we play with the mapping of the Zen hypervisor, namely in the translation that is performed not between the virtual to the physical, but from the physical to the machine, if I'm not mistaken in the Zen terminology. I mean the real physical one, the lowest translation stage. Well, we can offer cache partitioning via software without any impact, any visible impact on the guest VM, because it's everything I would like to tell you about a couple of challenges that we are facing in this effort. This is, I think, a nice venue to have feedback. So there are a few challenges that are related to x86. One is the fact that the mapping function may change from hardware to another. So I think here the only solution is to patiently find what we can do and perhaps make use of not 16 or 32 colors, but just 4. Another interesting point is the overlap in the mapping function, in the cache mapping function, with the DRAM bank mapping function. Depending again on the hardware, you may or may not have the possibility, which may be this may be an interesting plus or a cons, depending on how well the two things match. I can also partition my memory in banks, so I may have separate bandwidth on between two VMs. This is interesting. Or I can waste some bandwidth because I'm doing the wrong thing. One other subtle point, which has been quite easy in Zen, was the support for the I/O MMU. We need to be coherent with respect to devices, and since everything is the memory management is centralized in Zen, it was really effortless to do so. Concerning, there are some more technical challenges that we have faced, or well, we are facing. One is to have a nice data structure to represent the memory pool. The body allocator is something which hasn't been touched for years in Zen, I guess. And if you think about coloring with the body allocator, you realize soon that having a nice structure, a nice tree structure to manage huge pages and to maximize contiguity in your memory allocation is something almost completely useless in our setting, because we are striping the memory, so there is little contiguity. The thing we are opting for is to have a new data structure to store per color information, or perhaps it will be something per domain, so that I don't know, the first two colors are together and they can be allocated together, something which might be more efficient than a plain linked list. Another nasty bit will be, I say will because this is still in progress, coloring Zen itself, because we need to protect also portions of the hypervisor itself. Namely, there are portions involved in virtual interrupts, and those are very critical. The idea here is to have a hot reallocation to be done right when the second stage of translation is performed during the Zen boot process, namely when the second when Zen starts living as a true hypervisor. One last easy thing is to manage the ballooning. Of course, it doesn't. It should not mess with our colors. Here, I'm showing you a few numbers. Those were taken on Zen. And I'm comparing what happens between three configurations. So bare metal, on top of Zen or on top of a colored Zen. Our application is a very instruction sensitive one. It's just arithmetic instruction, purely register. This is meant to be as representative as possible to one of the consortium partners. And since I should have included another picture. Since we have our L1 instruction and a dedicated L2 as well, if I want to if I want to place my environment, if I want to place my test into the worst case, I need to do something to make the L3 availability as a need, as something needed. So on the same virtual machine, together with the benchmark, there is another application which periodically evict lines from L1 instruction and L2, so that the real interesting bit is in L3, so I can see whether the shared cache interference poses a problem and whether coloring comes into the play. So those are the three configuration without any stress. What happens if we add this interference? Well, we are here with just one competing core. We are using the null scheduler, and it was a 4 core machine, so we can add up to 3. And here we see that dramatically, in the case with 3 interference, numbers just explode. Instead, of course, with coloring, everything is fine. It works, right? Nothing unexpected. That's very good. Good. I want to mention a few ongoing things, more in the medium or long term, that me and my lab is doing. One is related to memory bound. Future ARM architecture will offer something to tune, to allocate bandwidth availability. There are also software techniques that we can add to the framework, so to have again a uniform, predictable memory controller interface. One other bigger topic is to add memory scheduling. Since the bottleneck is often there, why don't we reverse our perspective and we force our program to have a coarser grained structure, so long memory phases and long computation phases kept separated, so that a computation phase uses only local cached memory or partitioned cache memory, and memory phases are gathering all the prefetch or write back operation in one single interval. Well, this is very nice for schedulability. This is nice for analyzing the system. This is called the predictable execution model, and we already presented something about it with the help of a compiler, and I believe this might be an interesting direction in the future, also for Intel-like architecture. Last point is related to this hidden cat. I would like to spread the word about this. This is an interesting hidden feature, and this is very useful. So we want to analyze better where is available or where it's not. Perhaps it's an easy hack, very easy. Perhaps integrating in Zen itself. So that's all. I just want to invite you to come and see a demo organized by Evidence. You will see a nice EtherCAT motor, an EtherCAT controlled DC motor, and running, of course, on top of Erika, on top of Zen, in a predictable way. Thank you for your attention.
Okay, so there's going to be lunch served in 10 minutes, same room over there. Just to mention that there are a few people that didn't register for tonight evening dinner social team, so if you want to join, please come to me and I'll add you to the list, or I can add you to the list if you cannot join anymore. And I guess, yeah, we'll have lunch and then...